Distinguished laureates, ladies and gentlemen, good morning and very welcome to the House of Sweden and Embassy of Sweden. My name is Karin Olofsdotter. I'm the Swedish ambassador to the United States, and this is actually the best day every year at the Embassy of Sweden. Because the United States always produces Nobel laureates. That doesn't happen in every country. And so you are so welcome. Really congratulations again. So, as I said, warmly welcome to this year's American Nobel Laureate Symposium. And we have made it a tradition to welcome the American laureates to the Embassy of Sweden, which of course gives us all a great chance to learn about science from the best and the brightest there are, namely the laureates themselves. We will see how much we understand, though, later. This is also an opportunity for us who are not experts in your specific fields to try to understand, as I said, how their work and for which they have been awarded will affect us and our daily lives. Today, 4 out of the 6 2018 Nobel laureates are present, and you have all done amazing things in medicine, chemistry, and economics. So for medicine, we have Professor James P. Allison. Arthur Ashkin could not attend today. For chemistry, we have Professor Francis H. Arnold and Professor George P. Smith. And for economics, we have Sterling Professor William D. Nordhaus, who couldn't be with us today, but we have Professor Paul M. Romer here. So congratulations again to each and one of you, and of course to your families and friends that have supported and encouraged you during all the years of successful research. So during this day, the laureates and their families also have a chance, of course, to meet each other. Some of you have worked together, so you know each other very well, but cross-disciplinary friendship can also be beneficial. And you will learn a bit more about what to expect when you go to Stockholm for the week of celebrations around the award ceremonies. So you can actually treat today's symposium as a practice run in Stockholm, for Stockholm. Well, today it is very important to emphasize that knowledge and science is borderless by nature. It's a process that benefits from sharing ideas across borders and nations. And this year's laureates are a true example of this. Facts and science has got a big role to play in uniting people, creating a sustainable future together. That's very important, regardless of religion, origin, ethnicity, or gender. And this is also in line with Swedish Alfred Nobel's thoughts when he established the Nobel Prize. He said, "It is my express wish that when awarding the prizes, no consideration be given to nationality, but that the prize be awarded to the worthiest person, whether or not they are Scandinavian." Well, a large part of the Swedish economy is dependent on international trade and exchange. And research, development, and innovation has been the core of Swedish society ever since the days of Alfred Nobel. And Sweden is actually one of the most research-intense nations in the world, and the World Economic Forum ranks Sweden as the second most innovative country in the world. And one example of the innovation can be seen here today. We thought we would have the beer-serving robot or the coffee-serving robot, but you can, in the back of the room, meet their friends, Robot You Me, from the company ABB, and it's also ABB who does the coffee-serving and the beer-serving robots, but they were not available today. And new for this year is that ABB and Nobel Media have announced an international partnership which brings together 2 respected organizations committed to the development of innovation, education, and scientific research. So we are very happy to have ABB here as one of our partners for this event. Of course, I would also like to highlight our other partners for the year. IKEA, IKEA USA that is, Volvo Group North America, Saab North America, Axis Communications, Barbara Osher, Pro Suecia Foundation, Volvo Cars USA, and Absolut Vodka, and of course the members of our advisory board. So today we bring the laureates to the spotlight and let them inspire us and others around the world. You might have, I don't know, but maybe you have already noticed that people are globally interested in your opinions on a lot of matters, not just about your research. And we certainly look forward to today's symposium. We are also live streaming this event. So if you are looking at us from home and want to join the dialogue, please do so by using our hashtag SWENobelUSA, and our handle is Sweden in USA. For several years, Dr. Alan Leshner has graced us by moderating the symposium and the discussion. Dr. Leshner is the former CEO for AAAS and has had a long and distinguished career at the National Institute of Health, the National Science Foundation, and in academia. So I'm extremely happy to welcome you back. We hope every year that you will continue to help us out and moderate the seminar. So we are extremely grateful that you're doing it this year as well. I know you are busier than ever, so thank you for taking your time. So thanks, Alan, for being here. And now the floor is yours.
Thank you. And if you misbehave, I throw this. Excuse me, just a minute. So, good morning. Good morning. Okay, so this is also my favorite day of the year. I love this event, so if you don't mind, good morning. Good morning. Thank you. Okay, well, I really do look forward to it, and I think we'll benefit greatly from what we hear from the Nobel laureates this morning. My job is to set the stage, to make sure everyone behaves. Good luck, Alan. And I do want to give you the ground rules, okay? Some of you have been here when I've done this before. The rules change a little bit from year to year, but not a lot. The first rule is this is the best room in Washington with a fabulous view. You may not be distracted by the view. Therefore, I would ask that everyone look to your right. Isn't that nice? Don't do that again. Second, as the ambassador said, this is being live streamed, and so when you do get to ask questions, you're going to have to use the microphones so the people who are watching can, in fact, hear what's going on. And then there will be an opportunity after the laureates give us a little bit of an introduction to their work where you get to ask questions. I always like to define a question. A question is something, it does not have a preamble. Your voice goes up at the end, and it's short. Okay? And those of you who know me know that I am shameless, and if anyone goes on too long, I'll start making terrible sounds. And so I ask you to keep that in mind as you prepare your questions. We are collectively extremely proud of the laureates and their work, which is tremendously important. And the instructions that they've been given is to take a couple of minutes to tell you what they've done and then tell you why you should care about it from their perspective. And then we're going to open the floor and have at them, as we say. All right, we'll start with Dr. Allison.
Thank you very much. For about 30 years or so, I've been studying regulation of T cells, which are the arm of your immune system. That's the soldiers, if you will, of the immune system. They go all over your body and look for stuff that ought not to be there, virus-infected cells, or in the case of our work, cancer cells. And what we learned over the years was that it's not a simple thing of just flipping a switch. It's got one master signal. It's called the antigen receptor that recognizes that foreignness in cells. But there's another one called CD28 that we showed in the late 80s. It's like the gas pedal. It's a second signal that a T cell has to get going. But then it turns out it's even more complicated than that. It was thought for a long time that once the immune response had run its course, the cells just died, and some of them stayed around as memory cells. But what we learned was there's another molecule called CTLA-4. You don't need to remember that, but it's the brakes, and when the response is over at a certain point, it actively stops T cells in a cell-intrinsic manner. It tells them, don't divide anymore, kind of go away. You have to have that to protect you from damage, your normal cells being damaged. Well, when we found that out, I had the idea that if we disable the brakes for a short amount of time, that maybe, in the case of tumors, if the immune system gets turned off too early, the tumor wins. But if we could just keep the T cells going for a while by disabling the brakes temporarily, we could give the immune system a chance to kill tumor cells. And so we did a lot of work in animal models and started with melanoma and did the first trial that led to approval was finished in 2010 or so, and it was approved. This drug, ipilimumab, was approved by the FDA in 2011 for the treatment of metastatic melanoma, and is now available to everybody. It turns out there are other checkpoints as well, one of which PD-1 was discovered by Tasuku Hanjo in Japan, who shared the prize with me. In any event, they work together very nicely, and if you combine those two, in melanoma, 60% of patients have a durable response that lasts at least 4 years. In the case of melanoma, there are many patients who are 10 years plus out. About 1/5 of all patients who get a single treatment are alive 10 years after a single treatment. And now these drugs have been approved by the FDA, not just for melanoma, but also for lung cancer, kidney cancer, bladder cancer, Hodgkin's lymphoma, head and neck cancer, Merkel cell cancer. I won't go on and on, but you get the issue that it's a way, since you're treating the immune system, not the cancer cell, it has the opportunity to treat all cancers. And it's really not quite that simple. There are some limitations, but Pam Shorm and I, my wife, are working to extend it to as many cancers as we can, and by understanding the mechanisms, and so that we can bring cures to more patients.
That's great. Thank you. I don't want to put pressure on the rest, but I actually understood that, and so I appreciate it. Dr. Arnold.
Breaks.
Thank you, Alan. Thank you, Ambassador, for inviting us to this celebration of science. It's really wonderful to be here. I'm a chemist who is fascinated by the chemistry of the biological world, the best chemist on the planet. But as an engineer, I'm also fascinated by how nature creates this chemistry and the design process that she has used to make all of the beautiful biology that we have around us, and that's called evolution. Now, human beings have used evolution by artificial selection for 10,000 years to modify the biological world, making everything from corn to carrier pigeons, lab rats, racehorses. We've been modifying DNA to make things that serve us and that give us pleasure. I do that with molecules. I have enjoyed, for the last 30 years, recombining DNA, mutating DNA in the test tube, breeding molecules like you breed cats and dogs. And with that, we can create chemistry. We can create the catalysts that biology didn't care about, but that human beings might be able to use to move into a much more sustainable future. So imagine doing the chemistry that we do now with chemical factories and pulling oil out of the ground. Imagine doing that with renewable resources in clean biological processes to make the chemistry that we need in our daily lives. So that's what I do in the laboratories. I try to breed these molecules that will solve problems that human beings care about. And it's a fascinating process to see how rapidly the biological world, the product of 4 billion years of evolution, can innovate and move into the future if you just give her a little bit of push. So that's what I do. I push nature.
This is going to be a great day. I can tell already. Dr. Romer.
I cede my time to that. If you listen to the way they just describe what they do, it's emblematic of how science always works. We have the kind of the very deep, detailed specificity of like metastatic melanoma, but then also these abstractions like evolution and a rugged landscape. And we think about that in biology, and then suddenly those same abstractions turn out to be useful in another place. Now, my role as an economist was mostly in that realm of the abstractions that help you see sometimes unexpected connections. And I started with some of the very simple questions in economics, like what does an economy do? Well, an economy produces goods. Okay, well, goods are good, I guess, so that, you know, and you don't want bads. There's a lot of just junk, but okay, we produce goods, great. Okay, so we've got some set of goods like that kilogram of copper. And there's some process that leads to the production of a kilogram of copper. I got that. But then what kind of a good is it to discover that if you mix copper with tin, you get bronze, which is much more valuable than you'd get if you just had the copper and tin separately? So if you distinguish the kind of standard goods from ideas, discoveries, whatever we call it, mostly what I set out to do was, or what I did to answer a question, I'll explain the question in a second, but I was forced to think carefully about what kind of a good is a discovery or an idea, how does it differ from like a pound of copper, and then how do we think about how we cooperate as humans to get more stuff that's good. The question that got me thinking about this was a historical question, not immediately a policy-related one. If you look at the long sweep of history, what you see is that by any measure, the rate of progress has continued over time and has actually been increasing it's been progressing at a faster and faster rate. So when I first started asking this question, people thought I was really just totally out to lunch because it was the time of the population bomb and limits to growth, the stagflation, if you remember the late 70s. And I was looking at history and saying, gee guys, I mean, things are getting better and better, faster and faster. Like, you know, what's everybody so worried about? And I think what was going on was we were overreacting to some short-run difficulties we faced, and then translating that kind of pessimism about the short run into the long run in a way that I just thought was totally misplaced. I think if we do the right things, we can take advantage of all of these possibilities that the world creates for us. We can guide that search. We can speed up the search for things that we think are good. And we could all grow, continue to grow, even grow faster in the future than we've grown in the past, or have progress in the future that's faster. Now, the kind of unexpected wrinkle in this is that then you have to start to think, well, what do we mean by progress? Is it just like bigger houses? You know, and one, do we care that much about that? And two, is that sustainable? In this world of just the stuff, there's only so far you can go with kind of pulling copper and tin out of the ground and trying to do something with it. Eventually, it's going to get harder and harder to find. And it also, so this is kind of the insight of Malthus that goes back, you know, hundreds of years. Things are going to get worse if all we're doing is working with a fixed amount of stuff. And also, if there are other people, that makes it worse faster, or it makes it, if there's the number of people growing, it makes it worse faster because there's only so much copper that we're going to have to divide up amongst ourselves. So if you think about a broader notion of human progress, it sounds pretty grim. We're not going to be able to keep having, you know, more of the stuff we like, and we're going to be at each other's throats because we're going to be fighting over a limited amount of scarce resources. When you realize that value comes from discovering ways to take the stuff we have and turn it into something that we value much more, and then you start to think about analogies like you know, protein sequences or, you know, chemical formula, you realize that there is this just incomprehensibly large set of things yet to be discovered. We just can't possibly have found everything that would be valuable. And if they have this special characteristic, a discovery has a special characteristic of these types of ideas, that once somebody in the world finds it, everybody can benefit from it, that completely changes what it means to be a human. Now all of a sudden, it's good to be part of a billion people instead of a million. It's good to be part of a world with 10 billion instead of a billion, because there are more people who will eventually go out and discover those things. And once somebody finds it anywhere, we can all benefit from it. So the thing that will keep material progress going is this potential for just finding more and more ways to use stuff from the atmosphere and the crust to treat cancer and do other things we care about. But the real progress, the real human progress, will come from this recognition that we actually value everyone, that we can all be better off, and we're helped by the presence of all of those people. And if we can keep that in mind, it gives us a chance to not only have the material progress, but this more important kind of human progress in which we become the kind of our better side is enhanced as we look into the future. So I've always been at risk of being drummed out of the economics profession because I'm so optimistic, but I just can't help it. That's just what the facts tell me. Now I should be honest. There is a glitch here. The decisions, I've talked about conditional optimism, like you can't be complacent about anything. It takes the right decisions to make things get better. The most important decisions are those that operate at a collective level. There's a lot of things we can do as these kind of heroic individuals, but there's very important steering for the system as a whole that has to come from collective decisions. And it's very difficult to get people to reach a collective decision and then to stick to it. So there's good reason to be pessimistic about a lot of issues right now because of this difficulty of getting us to agree and decide what to do. And often, it doesn't really matter that much what we decide. We just decide something and do it instead of keep fighting over it. So there's reason for being concerned, but I still think the physical world, this amazing physical world that we inhabit, creates these enormous possibilities. Humans have had, trouble cooperating and exploiting these possibilities over time, but we've sorted it out in the past, and so even recognizing the real challenges we face about making decisions as in the collective or as a group, I still remain optimistic. So if they want to drum me out of economics, so be it. I'll join chemistry and physics.
Thank you for that note of optimism on this rainy day. That really is encouraging in and of itself. I do have to make the comment that I've noticed over the years that very frequently Nobel laureates get the prize for ideas that have worked out that other people earlier on thought were ridiculous. So we're happy you didn't get fully drummed out of economics. We benefit from it. All right, Dr. Smith.
Phage display. I'm sorry for my voice and the cold. I'll do as well as I can. So phages are bacterial viruses. They consist of a chromosome wrapped up in a protein shell, and the protein shell protects the chromosome and also mediates infection, the ability of that phage to find, attach to a specific target bacterial cell, inject the chromosome inside. Once the chromosome is inside the cell, its genes program the cell to make many more copies of that phage particle and mediate their release out into the environment so that they can go on to infect other cells. So a typical bacterial phage, including the one that phage display was mostly exploits, would take about an hour for a cell infected by a single phage particle to release 100 particles, each of which can go on to infect a single cell. So we have 100 infected cells, and An hour after that, we have 100 times 100 infected cells, et cetera. So this is a huge population explosion. Of course, it can't last forever. You run out of cells. Cells might get tired and stop making progeny phages. But still, for the class of phage that phage display is mostly used, a single infected cell in a liter culture might end up with 10 to the 15th phage particles in that liter afterwards. So 10 to the 15th is, okay, so 10 to the 9th, 10 to the 6th is a million, 10 to the 9th is a billion, 10 to the 12th is a trillion, and 10 to the 15th is a gazillion or something like that. So it's huge, all right? And also, I'm not going to explain this, but that ability to replicate tremendously also allows you easily to clone a single phage particle and make a huge population of phage particles that derive from just a single particle. Okay, display. Display, to explain display, I have to say that it is completely easy by very standard recombinant DNA techniques to add an extra piece of DNA into the chromosome of a phage or any other biological DNA molecule. That chromosome can then be introduced to a cell artificially, not the efficient infection process, but an artificial, very inefficient process, but it doesn't matter. So you now have a modified phage that has a little bit of extra DNA that codes a guest protein, a guest domain, let's call it a domain, that is becomes part of one of the coat proteins on the outside of the phage. So that extra domain is displayed on the surface of the phage particle. That's where the term phage display, which I didn't invent, I think it was Jim Wells that invented the term, but I think it's an appropriate term. So why is phage display important? Well, the fact that that extra domain is displayed means that anything that interacts with that can still interact with it, even though it's part of an infectious phage particle. So let's take a particular example. We have an antibody that binds to that guest domain on the surface of the phage particle. If that antibody is immobilized, let's say on the surface of a petri dish, and the collection of phage particles is poured on that petri dish, then the domain, the guest domain, binds to that immobilized antibody, and you can wash that petri dish to your heart's content, and the phage are still captured on it by virtue of that interaction between the immobilized antibody and the extra domain on the phage particle. And those phages can then be released, retaining their ability to infect, and can be propagated to uncountable numbers in the way I just described. So I haven't finished yet, though. So I have to describe one more thing that makes phage display a widely used and, as it turned out, very important technology that I absolutely did not anticipate at the time. The same kind of technology that introduces a single guest domain to a single phage can be used to introduce billions or trillions of guest domains, different guest domains, onto trillions of phage clones, so that you can create a collection, a sea of phage particles containing hundreds of billions or maybe trillions of clones displaying hundreds of billions or trillions of different guest domains. So let's say you have some target and you have no idea how to create a guest, some kind of guest domain that would bind to that target. Well, if you create a big enough library, perhaps somewhere in that library there will be a guest domain that will bind to your target. Your target might be, say, a receptor for involved in cancer or some other thing like that, or involved in autoimmune disease. So even though you have no idea of how to create something that is bind to that receptor, by immobilizing the receptor onto a petri dish and then pouring this collection of, say, 100 billion or a trillion phage particles on it, displaying 100 billion or a trillion different guest domains, the tiny number within that 100 trillion, that 100 billion or trillion that have that property of being able to bind to that receptor get captured on the surface. You can wash all the other ones away, throw them down the sink, and then the few that have remained can be released. And that is a way, without any prior knowledge of how to create something that will be captured by that domain, you can discover a domain that will capture that will bind to that capture molecule. So one of these libraries, which would take up maybe 10 or 15 mils in a little bottle, might contain something that will cure this kind of cancer, or that will help to alleviate an autoimmune disease or something like that. I myself am not responsible for any of that technology, but a number of scientists have understood how this kind of technology can be exploited to create molecules with desired activities. So I think the most famous thing in which phage display has played a role is Humira antibody. So for some people, it's like a miracle cure. It's a miracle drug. And this is something absolutely that I had no way of anticipating. And I think that's how science works. I mean, Paul has been talking about how ideas are produced in the process of our economy writ large, including our academic economy. And these ideas are taken up by other people as if they were themselves phages that go infect people, and they infect them in a good way. So in a nutshell, I think that's what phage display has been useful for.
Thank you. I would call that a phage-centric view of the world. I sort of like that. All right, we're going to open it up. Again, there are microphones. Someone has them, and they'll come to people who raise their hands. I would remind you of the rules about questions, and I would ask you, don't make them too technical, because some of us may not be able to fully grasp it. This was great. Thank you again for doing that. Okay, who's got the mics? I see somebody here. I see the mics there. There's somebody there and somebody here. And again, please just wait until the microphone comes right here. Yeah.
Good morning, Sanjin Choi, Langham Partners. May I address question to Professor Romer? Since you are recipient of a Riksbank's prize, my question is A, what is your views of an e-currency project? B, what are the technical difficulty of implementing e-krona? Thank you very much.
So the question is, what are my views about e-currency, of which I think Bitcoin would be an example that people might be familiar with. It's a good place to emphasize this point about individual effort as opposed to group decision making. In the United States, we have a group outcome, which is some legislation that creates the Federal Reserve Board and the banks, and then a board with a chairman chairperson who can make decisions very quickly about interest rates. And the speed of that decision making is very important when you face the risk of a crisis. The conjecture that some people have had for a long time is that the group level structure, the power of the government, the police powers, the elections, all of that could be dispensed with, and we could go back to some kind of imagined world where every individual is free to be creative, and there's no government or no process that could oppress the individuals. And so Bitcoin was the first implementation that held out that kind of prospect. You don't need a Fed, you don't need a central banker, you don't need any human with any discretion, you just write the rules. It's this once and done solution to the problems of cooperation. And if you followed Bitcoin, you know that it was only a few years before the rules broke. And it turned out that you cannot solve these complicated problems of cooperation at scale. In the beginning, no person can anticipate all the things you're going to run into. It's this complexity of the search and the environments we're going to face, which mean that we're always in a kind of evolutionary or adaptive mode. So the idea that we can get rid of government and just have code that will do all we ever need to do to structure our interaction, I think is just kind of a delusion, to be honest. So some people have made money in Bitcoin, but as a solution to this deep question about how do we govern ourselves, and there's no perfect solution to this governance problem, because any system that can implement decisions has police powers that could be used to subvert whatever accountability system that we try and put in place. So it's always a delicate process to keep collective decision-making working well and getting to outcomes that are good for everybody. But I think that what the search for these e-currencies will prove once again is that there is no once-and-done solution for complicated problems of human cooperation. We're always going to need adaptation. That's always going to require some human discretion and decision-making. On this, I'm more pessimistic than most of my colleagues, so take it with a grain of salt. But
yeah, I was just going to ask you what happened to your optimistic thing, but I get it. It's all right. Thank you.
I'm not optimistic about like the anti-vax approach to disease management either, so being optimistic doesn't mean you have to buy into everything.
Damn. Okay, you have a mic in the back.
Thank you. Also a question for Professor Romer. Getting back to the optimism aspect, I also like and admire your optimism. Do you think we have as much reason to be optimistic today about the problem of climate change as we perhaps should have had in the 1970s about the population bomb? How are these two issues similar to or different from each other? Thanks.
Good luck.
Yep. So I think I'm out in the tail on the optimistic side. When you look at the anticipations of what it will be like to solve an environmental problem, and then you look when we actually set out to solve it in a way where we allow some flexibility about what the solution is, I think in every important case, it's turned out to be much less expensive than we anticipated. So I think we routinely overestimate the difficulty, mostly because what we think about is choosing between the existing alternatives, which are typically pretty inefficient, and we just consistently fail to anticipate the solutions that will make adaptation much less difficult than we think. So what's critical is to make the decision to start going down that path and to trigger all of the discovery that will make it easier for us to adapt to. There's a few other things that you can use to put these things in context. If you just calculate any reasonable growth rate, 1.5% per year per capita GDP growth, and just think about how much richer we'll be in 30 years, 50 years, 100 years. If we had to spend a little more on transport and heating our homes and so forth, it really wouldn't be a disaster in a world where incomes are going to be increasing so quickly. So even if it's somewhat expensive, we could afford it. And in fact, I think it's going to be less expensive than people think. I've had this conversation with, I think, just briefly with Bill, because he and I have been inundated with travel planning for a whole contingent of people going to Stockholm since since we got the prize, but also with his son, Ted Nordhaus, who runs the Breakthrough Institute. And if you don't know about Breakthrough, it's a good source to look at on environmental questions, which is a little bit outside of just the usual conventional wisdom. I think I'm even more optimistic than Ted and Bill are. But how do we resolve these things? Well, they're just questions of fact that it's on the agenda for all of us to go look at. I looked at the evidence about what happened how did we address the ozone hole, and what Bill and Ted remember was that there was a particular kind of replacement for chlorofluorocarbons that was very important in refrigeration. And who knows, that maybe that was a fluke. But again, each time we look, we find solutions like that. My recollection is that a substantial amount of the adjustment was not by replacing the chlorofluorocarbons with this other chemical, but it was that we decided that instead of applying underarm deodorant with spray cans with chlorofluorocarbons, we used deodorant stick. So, that kind of stuff, there's a lot of that we underestimate. So I think once we finally create incentives to decarbonize energy, I think it won't be as, before ozone hole, it was like, the economy won't survive if we try and limit this. And then afterwards, it's like nobody even noticed what the adjustment costs were. So I think there's grounds to be optimistic, and we really need to guard against pessimism that leads to apathy and paralysis.
I'd like that to spread, that last sentence. Okay.
Infect that idea with people you know.
We can do it with a phage. Okay, who's got the microphone? There, please.
I'd like to ask Dr. Arnold perhaps a broader chemistry implementation question in terms of your experience both in the laboratory and entrepreneurially and interacting with industry that goes into economics, but I'd like your perspective from the science, from the chemistry side in terms of impacting the plastic non-renewables, and we've had polylactic acid. We've had a number of possible choices. What is your sort of view of where we're going to go in terms of the science and the penetration of the science to get more renewables that are not petroleum-based and that take advantage of nature?
Well, I think the future looks really good. The technology has gotten excellent. It's hard to make money at it when the price of oil is so low, and we as a society collectively do not decide to price its utilization at a level that would help switch these over. But the technology keeps getting better and better. So there are fabulous alternatives to pumping oil out of the ground and making at least many of the chemicals that we use in our daily lives, making jet fuel, for example. And there's a tremendous amount of innovation that's going on in this field of biotechnology that enables this to happen. I've been around for quite a while, starting with the Carter era, when we had as a country a goal of 20% renewable energy by the year 2000. That was a stated U.S. goal. I was a young engineer at the Solar Energy Research Institute when that happened. Change of administrations, change of oil prices, bigger cars, that switched. 2004, oil hit $150 a barrel. Everybody jumps on board to renewables. Fracking comes along, price of oil drops again, and in the meantime, all that technology is better and better, and I'm waiting for the third round to happen, and then perhaps that one will really stick. In the meantime, it's getting better, and we're doing a very good job with the technology.
Great. Okay. There.
What have been some of your professional failures, and how, if any, what role, if any, have they played in ensuring your current success?
Ooh, I like that question. Okay, very short. Short answers. Professional failures that have had an influence on where it's going. Anybody want to confess? Go ahead, Dr. Smith.
I confess to many professional failures, I think. I mean, after the original sort of development of phage display, my idea was to apply this to new ways of developing vaccine for difficult diseases like malaria. I made very little progress in that. I didn't get my NIH grants funded. And
We've all had that problem.
And I think that almost anyone in science, and I certainly can speak for myself, experiences many failures in their career, and some things turn out to be really important in ways you don't expect. But I'm not sure I learned a lesson from it so much as it didn't deter me.
If I could add something, I think that's universal amongst all scientists, I think. I mean, you make a hypothesis that's going to explain something, and if you're right every time, it means you're not asking the right questions. You're asking things that are obvious, and anybody can get them. It's when you're wrong that you know you're making progress, as long as you know why you were wrong, and it takes you down the road further to finding something that's correct. But science is about being wrong, actually. You can never prove anything. You can only fail to disprove it, is what it comes down to.
I like it. Okay, who's got the mic? Please.
I have a question to Dr. Allison. Since single therapies are seldom effective, what do you think the immunotherapy should be combined with? What kind of treatment?
Well, that's one of the nice things about immunotherapy is it can be combined with almost anything because the process is initiated, at least checkpoint blockade, is initiated by tumor cell death. And so that's ultimately where it all comes from. That's what alerts the immune system that something's there, and it enables the whole process that leads to priming T cells get started. And so there's been tremendous combinations and results from combining it with chemotherapy, some chemotherapies with radiation therapy, a little bit of work with the genomically targeted agents. And so there's so many possibilities. It's very difficult to deal with them all now, and a lot of them are done empirically. But what it's going to take to really do this efficiently is for the people who are used to with radiation therapy or with chemotherapy, they think they got to kill every last damn tumor cell. They just got to bomb it and bomb it and bomb it. Realize you don't have to do that with immunotherapy. You just have to kill enough to alert the immune system and back off. And we're going to be able, I think, to decrease side effects while improving response rates and durability when we find the right ones. The thing that we have to do along the way, though, is learn from every combination that's tried. And if they don't work, we need to still analyze the tissues and things and figure out what was missed, and then do only big trials with the rational combinations that have a mechanistic reason for being successful.
So I can't control myself. I apologize. So you mentioned two of what I think are the hottest areas in medicine today. One is immunotherapy, and the other one is genomic medicine. And the notion of personalized medicine as opposed to a therapy that could, in fact, affect many, many different kinds of cancer. What's the intersection of the two?
Well, I think there are going to be cancers that respond to just immunotherapy, but I think the intersection would be some of the ones we're not getting a signal in now, for glioblastoma, pancreatic cancer, and things like that. And I think that it is going to have to be personalized, I think, because there's an array of checkpoints as well that are distributed differently amongst different kinds of cancer. So there's going to have to be, it starts off your immune system's pretty personalized after all anyway. But you can even make it work better by paying attention to what's going on in each individual patient.
All right.
Could I just make a point on that? At the level of abstraction, this idea of heterogeneity and not just looking for an average effect is an extremely broad and important idea. If you think about teaching kids to read, if you have an intervention, you want to look not just at what does it do to the average performance in the population of kids, but what in particular is it doing for this subset who end up with dyslexia or just fail to learn to read. There are very small differences in individuals that can set these conditions up. Very simple interventions at that stage can get them on this same explosive trajectory of reading and mastering of orthography and so forth. So like the right intervention there could be very influential in reducing the inequality of educational attainment. But if we're just focused on average performance, we're just going to completely miss the chance to address this.
Great. Who's got the mic? I can't see. There it is.
There we go. Billy Liserson, BL Insights. I'm very interested in the public understanding of science, and in particular the process of science. And I wanted to follow up on something that Dr. Smith said to ask you all a question, which is,
good.
Right now, you have, we see a lot of the applications for the work that you've done, but he mentioned that early on he had no idea that these applications would be forthcoming. And so if you would you comment on what you thought you were working on at the beginning that led to the insights that now we have for cancer, or for energy, or for the environment, or whatever?
I can start. When I started working on this, I take it back to when I was an undergraduate. I took an immunology course, and T cells had just been discovered, and all we knew was they went around the body and kill stuff. And how they did that was complete mystery. So I had some thought, but very little thought about cancer. I was just trying to understand how T cells worked, and then, as we learned more and more, then how we could use it, in a way became obvious after we understood the basic biology.
Go ahead.
Good morning. Teresa Williams. I'm also a recent Cal PhD graduate in chemistry. And I think that for maybe some of the younger scientists in this room, I'm sure that mentorship has played an important role in your careers in helping you overcome times of struggle. So what was the best advice that you might have received from a mentor in those times?
Whoa, I like that.
Well, I guess I could start. I worked with two mentors. I'm going to focus on Oliver Smithies, who was my postdoctoral advisor. Oliver Smithies was someone who got the Nobel Prize in, when was it? Does anyone know? I can't remember what year. But he was a mentor that really believed in academic freedom, including in his postdocs. So he was a mentor that talk to you about your ideas and let you run with them, and that was really important in my life. And I tried to emulate him in that respect, and I would say that I didn't exactly do that, but I really admired it in a person.
Anybody else?
Well, I'm not sure where I pick this up, but the advice I would give to people in science, one is that if you think about making an accomplishment in science as like succeeding in a market, you may not want to go into the most competitive market. That if all the conventional wisdom and all the senses on this, you might look around and just see, is there something else where people aren't doing as much work? Because I think that those areas tend to have a higher expected return. People are a little afraid and the returns are high. But you need to link that to this kind of idea that was implicit, I think, in all of our talks, but that in the venture capital business, they refer to as just fail fast. So if you're going to go out on a limb, just be quick. Just recognize when it was a mistake, and just give up and go try something else.
And actually, mine's a recombination of both of these, because my mentor, my PhD advisor, was smart enough to know that the biotechnology industry was going to be a very interesting place for engineers. This was a whole new thing in the 1970s. But he didn't know exactly what were going to be the interesting things, so he said, go figure it out. And that gave me the confidence, that experience of having to go figure it out, gave me the confidence to try it again and again. And that freedom, when you're young, right, to give a young person the freedom to create, not tell them exactly what has to be done, but that freedom to create is an experience that they will carry with them throughout their careers. So I thank my PhD advisor for choosing the right area, a growing area, and then giving me the freedom to do it.
That's great.
This is one of my hot buttons. we often talk about, listen, we're so bright, leave us alone, we'll do great stuff, we have no idea how it'll turn out to be useful, but just give us money and leave us alone. And there's something a little bit self-serving about that.
You think?
And this kind of attention, like, oh, there's this thing called biotechnology, let's pay attention to that. This is a really important part of science as well. It's just think about where the action is, think about where the practical payoffs are going to be. So don't get too caught up in this, we're in the ivory tower, leave us alone. There's a lot of interesting things going on.
Jim, did you want to add anything?
I think it was, I can't name any single mentor that was, but my undergraduate advisor was one very like here, but he would say, have an idea, and he'd say, well, go work on it, and I guess one of the most inspirational was my immunology professor, Bill Mandy, who just said there are these T cells. I don't know anything about them. You ought to figure it out. He was a B cell guy, by the way.
That's great.
There's an in-joke for you.
Did you have a question before? Okay, you're on.
Alex Simonian, National Science Foundation, this to Professor Smith. What do you think about perspectives to use phage and phage display to replace antibiotics and struggle bacterial infection? Thank you.
We'll take the short answer to this. This one could be technical.
Well, I'm not sure it's going to replace antibiotics. That seems unlikely. That really expensive development is going to be what's really required for antibiotics. Personally, my view is that we should be handling antibiotics by managing antibiotics more intelligently than we are, and also by investing in research that's going to give rise to new antibiotics as a public good, not as a money-making adventure. I mean, we desperately need. The world needs antibiotics for things like malaria, and there's no money in it, and so I'm not sure that phage display in particular is particularly relevant to that to that kind of problem.
So we have very little time left. Short answer. Short questions. Short answers. Okay. You have a mic.
Yeah. My name is Jim Whitty. I'm director of the Institute for Immigration Research at George Mason. My question builds off the ambassador's opening remarks about science knowing no borders. And this question is for any or all of you. How has international collaboration, as U.S. laureates, how has international collaboration advanced your career?
Short answers.
Short answer. Evolution teaches you that if you're not diverse, you go extinct, right?
All right. Wow. I really like that, Doctor. That was great.
If I could say, this point I was making about having more and more people who can all engage in search, that only pays off if there's some way to coordinate and stay in touch with each other. And, mobility, face-to-face interaction is part of that, but the book, the internet, publication, all of these are parts of how we share this kind of knowledge that has this capacity for sharing. And so we need to keep all of those working.
Okay. Quick. Yeah. Do you have a microphone or just a hand? You have one. Okay.
Several people have mentioned evolution. Is there room for evolution in the Nobel Prize? We have the traditional fields of physics, chemistry, but a lot of our problems, climate change, colonizing Mars, being an interplanetary species, don't really fit any of those. So how do we move forward?
It does fit. I'm an engineer, but I got the chemistry prize for evolution.
I like it. All right. We can take a couple more.
I think Rutherford got it for chemistry as well. So,
Yeah.
Okay.
We use that as a selection all the time. I mean, that's basically where the whole idea of the immune system comes from. I think you can't pull evolution out as an individual thing. It's everywhere.
And in economics too, there was a prize.
Okay, guys.
Eleanor Ostrom.
Guys, I want to get a couple more in. All right. Go ahead.
Hi, my name is Anna Gams. I'm a PhD student from George Washington University, and my question is, you cannot possibly think always about the science and the field you're doing. So what do you do to reset, and what clears your mind and inspires you to go forward afterwards? Thank you.
Really short. Go ahead.
I play harmonica with a blues band.
I like it. Dr. Arnold?
And occasionally with Willie Nelson.
Whoa. Now we respect you. Dr. Arnold.
I like to scuba dive.
Since January, I've been teaching myself Python.
Teaching yourself what?
Python. It's a computer. It's a computer language.
Okay,
but it's
sorry,
the best
guys.
one. So,
Go ahead.
Well, I've sung for a long time. I'm not a very good singer, but I've done that. I was a founding member in our community chorus from 1978, and I'm also pretty involved in politics.
For below.
All right.
I don't
Do we
know.
do
It's
it?
not recreation. Sorry. That's not recreation. The science is
All right. That's a fabulous note to stop on. Let's thank the laureates. I think it's been.
Well, and lucky for me, I don't need to have any hobbies to clear my brain because I have the best job. I get to do different things all the time and meet people like you. So I'm extremely fortunate. We just want to thank you, Alan, for your services today, and we are doing so by planting a tree in your honor for better environment in Africa. So we continue to do this now. For many years forward, you will have a whole forest. So thank you all for coming. Do come back. We are open on the weekends. We have great exhibits where you are sitting right now. We have a fun exhibit about Sweden and music tech and the Swedish music wonder, but also technology. Downstairs in our Alfred Nobel Hall, we have a great exhibit on Studio 54 in New York, one of the most famous nightclubs ever. And you might wonder why that's in a Swedish embassy, but the only one who got to take photos in there was a Swede. So for those of you who were there, maybe, and for those of you who would like to know what it was like, please come and visit us. So thank you so much for today. It's been wonderful to hear your stories about your research and your thinking, and it feels like the sciences are quite interconnected, actually, given what you've told us today, and that's a fantastic thing, making us evolve to be better people in the future. So thank you all for participating today. It's been a great honor to have you here, and do come back next year when I'm sure we will have new laureates from the United States. Thank you.